In the last couple of sections, we talked about flat data structures, such as records, arrays, and tuples. We can use them in our data computations. However, they are flat. That means we can perform only certain operations with them. In the upcoming sections, we will talk about variant types, which will improve the way we can process our data. We will also learn about recursive data structures like lists. Finally, we will talk about polymorphic data types. Let's get started with variant types. Let's say we want to build a tic-tac-toe game in Reason. In this game, we have two players, cross and circle. And these players are playing the game by marking fields on a playing board. In other words, we have two types of players who can mark a field on a playing board. Now, what's the best way to express this in Reason? And the answer is variant types, or variants. Let's define the player variant type first. As you can see, we define variants using the type keyword. The player variant type can be either cross or circle. It can only be one of these two options, nothing else. You can think of variant types as of enumerable sets of values, or enums. In more formal terms, a variant type can be also called sum type, or disjoint union of types. Variants enable us to take several types and join them into one unique type. In our example, we took the cross and circle types and joined them into the player type. We are now ready to use our variant in an example. We defined an identifier holding a cross value. The compiler is telling us that it has a type of a player variant, as you can see here. This means that we created the next turn identifier and constrain it to have a type of a player. And in exchange, we get this assurance that the next turn identifier will be either cross or circle. So if we will use our identifier in computations, we already know that we will need to write code covering only two scenarios, when the next turn has a value of cross or circle, and that's it. And this is powerful, since it makes it easier for us to think about our code, because we have this certainty what the player variant type might be. But what exactly are these cross and circle values? They are not strings, integers, or any other kind of type in Reason. They are called constructors or tags. The constructor identifier, like here, needs to be capitalized and must be unique and distinct. The constructors are separated with a pipe, like here. Each constructor in a variant type represents one specific type. In our example, it's cross and a circle. Moreover, a constructor can also hold a piece of data. Let's take a look at it by defining another variant type. We defined a variant field, which represents a playing board field in our hypothetical tic-tac-toe game. And each field can be either empty or marked. However, because constructors can hold data, we can make our variant much more specific. We passed a piece of data to the marked constructor. We are now saying that each field can be empty or marked by the player type, meaning it can be marked by the circle or cross player. You might notice that using a constructor with data is similar to a function call. It looks like we are passing arguments to our constructors, and that's why constructor's data is called a constructor argument. Let's take a look at another variant type. This one is called gameState, and we can use it in our game to monitor the state of the game. We can be playing, we can have a winner, or we can have a draw. As you can see, we are passing our player variant to two constructors. However, each of them has a different meaning. The first one is telling us which player is playing, while the other is telling us who is the winner. So, a constructor is helping us to distinguish between different usages of the player variant. So far, we've seen that variant types can be really useful, and we didn't even talk about their most powerful feature yet, which is pattern matching using a switch keyword. Let's take a look at an example. We still have our player variant, which can be either cross or circle. We also have the field variant, which can be empty or marked by the player. And we created a function toString, which takes an argument of type field and passes this argument to the switch, which will perform pattern matching. We defined 3 cases of our field variant. Year. If we compare the field variant type, year, with our new switch case analysis, we can see we covered all the cases of the field variant. This means that our pattern matching is exhaustive, meaning we are covering all the possible cases. The purpose of this function is to convert a variant to a string representing a particular constructor. If the field is marked by the cross player, we will return X. If it's marked by the circle player, we will return O. And if it's empty, we will return an empty string. As you can see, pattern matching allows us to check every possible case of a variant type. In other words, we are pattern matching its constructors. Pattern matching is basically a sequence of branches. First, we write the switch keyword here, followed by an expression having a type of a variant. Then we describe each possible case by a pattern followed by an arrow. Finally, we provide an expression for each possible scenario. There must be always at least one branch in pattern matching. However, this pattern matching is not limited only to variants. We can also use the switch keyword on most other reasons data structures, such as strings, integers, floats, or tuples. And this is one of the reasons why pattern matching using the switch is one of the most powerful features of Reason. Let's now call our pattern matching function to see how it works. We created an identifier random field, which has a type of a field variant, and it happens to be marked by the circle player. Then we pass this identifier to our toString function here. And the function performed pattern matching. First, it evaluated the value of the field here and figured out it's marked by the circle player. Second, it tried to match it with the patterns one by one. If the pattern didn't match, it tried the next one until it finally found a match. In our example, the first pattern failed. So we moved to the second one, which was matched, and we got back O, as you can see here. Let's now take a look at our toString function again. You can see that our pattern matching covers all the possible cases of our variant type. However, what if this wasn't the case? What if we commented out one of the patterns? Well, let's try that. Here, we commented out the last empty pattern, and the compiler responded with a warning telling us that our pattern matching is not exhaustive anymore. The compiler's warning is very useful because non-exhaustive conditionals are a common source of bugs in other programming languages. Well, we won't have these bugs in Reason, since the compiler will always tell us if our pattern matching is exhaustive. This exhaustivity check is especially helpful during refactoring, when you add a new case to a variant, for example. You don't need to go through your whole program, since the compiler will tell you which code was affected by this change. It will tell you that your pattern matching is not exhaustive anymore, so you can easily fix it, just as we can do in our example. However, this example is straightforward, since we have only 3 possible cases. Compiler's exhaustivity check is much more useful in more complex situations. Let's take a look. We defined an animal variant type, which has 3 constructors: bear, rabbit, and deer. Then we defined a function which takes 2 animal arguments and returns true if the animal 1 has a bigger size than the animal 2. We try to define patterns covering all the possible cases that might happen. However, because of so many possibilities, we are not sure that we covered all of them. Fortunately, we can ask the compiler. Let's run the code. The compiler is telling us that we forget to cover the rabbit and bear case. So let's fix it by adding this case and run it. So we added the missing case. When we have a rabbit and bear, rabbit is smaller than bear, so we return false. And if you run it, you can see we are not getting any warning from the compiler anymore, since we are covering all the possible cases in our pattern matching. You might notice that we are using an underscore inside the patterns here. By doing that, we are telling the compiler we don't care about this particular value. We just want to have a match always. Here, we know that a bear is the biggest animal, so we don't care about the second animal, since we know it will be always smaller than a bear. So we are telling compiler if the animal 1 is a bear, we want to have a match always. So thanks to the underscore pattern, our code is more concise since we don't need to write all the patterns explicitly. Another great benefit of variants is the combination with the type system. In our example, the compiler inferred that our function returns a boolean here. And this is another feature of pattern matching using a switch. Each branch will always return the same type. Thanks to this assurance, we can make states that should never happen impossible to exist. In our example, the only possible state that can exist is Boolean. So in our code, we need to cover only a case when this pattern matching returns a Boolean. We know for sure it won't return string or float or any other data type. We can make it even safer by returning a variant with predefined constructors from the pattern matching instead of Boolean. In the example, we use the combination of a tuple here and a switch. And this is very useful since it makes our code concise and easier to reason about. You can use this combination to get a readable list of all the possible combinations of values, and the compiler will make sure that you've covered all of them. Compared to if-else conditionals, where you are basically adding conditions on arbitrary cases, with the pattern matching, you are always covering all the possible cases. This ensures that whenever you need to refactor your code, you can target a specific case without touching the existing or adding new ones. As you can see, pattern matching using a switch is similar to switch from other languages. JavaScript, for example. In many situations, it's an alternative to if-else conditionals. For a comparison, let's rewrite our example in JavaScript using if-else conditionals. This is a very verbose piece of code, and we haven't even covered all the cases. We are still missing 5 cases. Compared to this imperative and verbose conditionals, pattern matching allows us to check every possible case of our expression using declarative and readable syntax. Moreover, the compiler will always tell us if our pattern matching is exhaustive, and we have this certainty that it will always return the same type of value. With conditionals in an untyped language, we don't have any of these benefits. Let's come back to our previous example. We have our function toString which performs pattern matching. However, we can also write it more concisely using a syntax shorthand. As you can see, we don't need to specify the argument of our function, and we also don't need to write the switch keyword. We just write fun keyword instead. However, we need to keep in mind that this syntax shorthand can be used only for pattern matching with a single argument. Cool! We know how to use pattern matching on variant types. However, we've mentioned that we can use pattern matching on other reasons data structures as well. Let's perform it on a string. We defined a random quote identifier containing a string which is a quote from the Star Wars. Then we defined an author identifier where we used pattern matching to find an author of the random quote. We are doing that by matching the quote using patterns. And we got back Obi-Wan Kenobi as the author. Moreover, we are using an underscore in this example again. And we've already mentioned that by writing an underscore, we are telling the compiler we always want to have a match. In this example, we are using it as a catch-all pattern or a default pattern. So when none of the previous patterns is matched, this default one will always match. Thanks to this default pattern, we don't need to specify all the possible cases. And this is useful since in the Star Wars movies there are thousands of quotes. However, whenever we use it, we are turning off the compiler's exhaustivity check. As a result, the compiler is not able to tell us that we forget to cover a particular case. So try not to use this catch-all pattern much, since it can be easily abused and might be a source of possible bugs. A good example of using an underscore is a case when you have almost infinite possibilities, just as we have in our example. In this section, we went through the variant types basics, and we will talk about variants even more in the upcoming sections, since in Reason we have two built-in variants, option and list.